Welcome back. In this video, we'll delve into some intriguing aspects of the dynamics of motion along a linear path. I'm sure you're familiar with the equation of a straight line. The general form of this equation is shown here on the screen. In this equation, x represents the independent variable, while y is the dependent variable. In simpler terms, changing the value of x leads to a corresponding change in y, as dictated by the relationship defined by the function. To jog our memory, let's identify 2 points on the graph, and label them as P1 and P2. The coordinates of each point are shown on the graph beside them. The gradient m of the line is calculated by the change in the y value as you move from one point to the other, divided by the corresponding change in the x value. This ratio of the difference in y and x determines the gradient of the line. Point C denotes where the line intersects with the y-axis, also representing the value of y when x equals 0. This represents the general form of a graph, allowing us to assign related but distinct quantities to x and y. For example, if we designate time as the independent variable and either displacement or velocity as the dependent variable, the nature of the graph changes accordingly. If we select displacement for y, the graph becomes a displacement time graph. Alternatively, if we choose velocity instead, the graph becomes a velocity time graph. We'll continue our discussion, focusing on the displacement time graph. In a subsequent video, we'll also explore velocity time graphs. By the end of this video, I'm confident that you will be well acquainted with the displacement time graph. Each term in the function must have consistent units. Since s has the units of displacement, the units of the slope m must be the ratio of displacement to time to maintain dimensional consistency. The gradient m has the units of velocity, indicating that the gradient of a function on a displacement time graph represents velocity. Since this gradient is constant, it signifies uniform velocity, meaning the object is moving at a steady speed without acceleration. With that introduction, we will now explore how to represent different scenarios using a displacement time graph. Alright, let's take one example at a time to understand how to use the displacement time graph. We'll start with a simple example and gradually move on to more advanced problems. In this first example, we have a vehicle that moves from point A to point B, with a constant velocity of 10 meters per second. The time taken by the vehicle to cover this distance is 50 seconds. Our task is to find the distance between the 2 points. First, let's identify the given information. We'll define displacement as positive when measured from point A towards point B, and consider velocity as positive when the vehicle moves from A to B. Since displacement is measured from A, and the vehicle starts moving from A, the initial displacement is 0. Therefore, the line on the graph passes through the origin at time 0. Given that the velocity is constant, and directed towards B, the gradient of the line is positive. With this information, we can draw the displacement time graph. The equation of the line under these circumstances is as follows. We can use either the graph or the equation of the line to calculate the displacement after 50 seconds. Whichever method you choose, the displacement will be 500 meters. What we need to understand is that when the vehicle moves from A to B, which we consider the positive direction of motion, the graph will be in the first quadrant. If the velocity of the vehicle is in the same direction as the positive displacement, the gradient of the graph is positive, and corresponds to the velocity of the moving object. Finally, if the vehicle starts moving forward from the point where the displacement is measured, the line will begin at the origin when time equals 0. Now let's look at another example. This time the vehicle is moving from B to A at a speed of 20 meters per second. We need to determine the time required to cover the 500 meters distance. First, we need to determine the quadrant where the graph will be located. The vehicle is moving towards A, and as before, we measure the distance from A to the vehicle. Although this distance is decreasing, it is still measured in the positive direction, placing the graph in the first quadrant. If the vehicle were to move in the negative direction, or to the left of A, the graph would be in the fourth quadrant. Next, we need to consider the direction of velocity. In this example, the vehicle is moving from B to A, which is in the negative direction, since we consider velocity positive when directed towards B. Consequently, the graph has a negative gradient, which corresponds to the vehicle's velocity. Now that we know the gradient and the quadrant of the graph, we need to determine the y-intercept, which represents the initial displacement. To do this, we need to know the vehicle's position at the start, or its displacement from the point of measurement, when time is 0. The initial position of the vehicle is given in the question as 500 meters. This is the starting point of the vehicle. Now, let's observe how the graph is drawn as the vehicle moves towards the point of measurement. As time progresses, the displacement value decreases, indicating that the object is moving back towards the origin of the coordinate system. Initially, the vehicle has a positive displacement of 500 meters, but this distance decreases until it reaches 0. At that point, the graph intersects the x-axis, or time axis. The vehicle is moving with a constant velocity, in the negative direction, which means the graph is a straight line, with a negative gradient. The steepness of the slope indicates the velocity. The steeper the slope, the faster the object is moving. With that in mind, we can now write the equation for the line. The vehicle completes its journey when its displacement becomes 0. By substituting 0 for displacement, we can find the time it takes to complete the journey. I hope this explanation was clear. Let's look at another example. This time, we'll combine the previous two examples to calculate the average speed of a vehicle's journey. When dealing with different speeds, the average speed is the constant speed at which you would need to travel to complete the journey in the same amount of time as you would when moving at varying speeds. A vehicle starts its journey from point P and moves towards point Q at a velocity of 50 km per hour. Upon reaching point Q, the vehicle immediately turns around and heads back to point P at a velocity of 30 km per hour. The entire journey takes 2 hours. We need to calculate the distance between points P and Q, as well as the average speed of the vehicle. The first step is to plot the displacement time graphs for both the outward and inward journeys of the vehicle on the same set of axes as time progresses. The vehicle begins its journey from point P when we start recording the time. We can use point P as the reference point to measure the distance of the vehicle and define the direction towards point Q as positive. Consequently, for both displacement and velocity, the direction towards Q is considered positive. The vehicle moves only between points P and Q, meaning that the distance from point P to the vehicle is always positive. Therefore, when plotting the displacement, both the outward and inward journeys are located in the first quadrant of the graph. When time equals 0, the vehicle starts moving from point P, meaning the displacement is 0 at the start. Therefore, the graph should start from the origin. The line's gradient represents the velocity, which is in the positive direction, so the gradient of the graph should be positive. Although we do not know how long the vehicle travels, we can assume the distance is s kilometers and the time is t1 hours. We can then mark a point on the graph with these coordinates and draw a line connecting this point to the origin. This line represents the displacement graph of the vehicle's outward journey. The vehicle turns around immediately and heads back towards point P. It begins its return journey from a displacement of s kilometers after t1 hours. As mentioned earlier, the displacement remains positive, since the distance is measured from point P, but now the vehicle's velocity is towards P, which means it is in the negative direction. Therefore, the gradient of the displacement time graph should be negative, and it should start from the point where the previous line ended, with a downward slope. Since the total journey time is 2 hours, the line should reach zero displacement after 2 hours, meaning it should intersect the time axis at the 2-hour mark. However, we do not know how long it takes the vehicle to return to point P. We can assume this time to be T2 hours. But what we do know is that the total journey time is 2 hours, meaning that T1 plus T2 equals 2 hours. The gradient of the red line, representing the velocity of the outbound journey, can be expressed in terms of s and T1 as follows. We can then rewrite this expression to solve for T1. Similarly, we can express T2 in terms of s. Since the sum of T1 and T2 equals the total time taken to travel between P and Q, which is given as 2 hours, we can derive a function in terms of the displacement s. When we solve for s, we find that the distance between P and Q is 37.5 kilometers. Before we calculate the average speed of the vehicle, let's understand the difference between average speed and average velocity. Average velocity is a measure of the overall change in position, or displacement of an object, divided by the total time taken for that change in displacement. It considers the direction of motion, making it a vector quantity. Average speed is a measure of the total distance traveled by an object, divided by the total time taken to travel that distance. Unlike average velocity, average speed does not consider direction, and is always a positive scalar quantity. Returning to the example, the total distance traveled by the vehicle is twice the distance between points P and Q, and the total time taken is 2 hours. Therefore, we can calculate the average speed between P and Q as 37.5 kilometers per hour. Now, let's consider the total displacement of the vehicle. Since the vehicle returns to its starting point, the total displacement is zero. Therefore, the average velocity is zero, because the vehicle's starting and ending positions are the same, resulting in no net change in position. Let's explore how the displacement time graph reflects the second scenario. Even though the total displacement is zero, because the vehicle returns to its starting point, the journey from P to Q covers a displacement of 37.5 kilometers in 1 hour, which is half of the total journey time of 2 hours. This gives a velocity of 37.5 kilometers per hour for the outward journey. Similarly, the return journey from Q to P also has a velocity of 37.5 kilometers per hour, but in the opposite direction. This results in a positive gradient on the graph, when moving from P to Q, representing a positive velocity, and a negative gradient when returning from Q to P, indicating a negative velocity. The graph visually captures the constant velocities during both the outward and return journeys, showing uniform motion with clear positive and negative slopes corresponding to the direction of travel. Alright, let's move on to the next question, which is an extension of the previous example. The only difference here is that the vehicle does not return immediately after reaching point Q. Instead, it remains stationed at point Q for 1 hour before heading back to point P. Our task is to calculate the average speed of the total journey. The displacement time graph initially shows a positive gradient when the vehicle moves from P to Q, indicating a positive velocity. When the vehicle remains stationary at point Q for 1 hour, the graph shows a horizontal line with zero gradient, representing no change in displacement. Following this stationary period, the return journey is depicted with a negative gradient, reflecting the change in direction as the vehicle moves back towards P. This displacement time graph is identical to the previous one, except for the segment representing the idling period at point Q. The new graph includes a flat, horizontal line during the 1 hour stationary period, distinguishing it from the continuous positive and negative gradients of the previous graph. The average speed is calculated using this formula. This equation includes all time intervals, even when the vehicle is not moving. So, although the vehicle is stationary at point Q for 1 hour, this stationary period is still part of the total time. While no movement occurs during this period, it must still be included in the total journey time when calculating average speed. We can calculate the average speed of the journey as 25 km per hour, which is lower than the previously calculated average speed of 37.5 km per hour, due to the 1 hour idling time at point Q. This reduction highlights how stationary periods, even without movement, significantly affect the overall average speed of the journey, by increasing the total time without contributing to the distance traveled. Let's explore another example, to better understand the difference between average speed and average velocity. In this scenario, a vehicle travels in a straight line from point A to point B, at a velocity of 10 meters per second, taking 3 seconds to cover this distance. After reaching point B, the vehicle makes a right turn towards point C, and continues its journey at a velocity of 4 meters per second, taking 10 seconds to travel from B to C. Our task is to determine the average speed and the average velocity of the vehicle over the entire journey. First, we calculate the total time taken for the entire journey, which will be used to find both the average speed and average velocity. The total time is the sum of the time taken to travel from point A to point B, and from point B to point C. The vehicle takes 3 seconds to travel from A to B, and 10 seconds to travel from B to C, giving us a total journey time of 13 seconds. Next, we need to determine the distances between points A to B, and B to C to calculate the average speed. For average velocity, however, we need to find the straight line distance between points A and C, as average velocity depends on the total displacement, not the path traveled. We know the vehicle's speed between points A and B, and the time taken to travel between these points. Using this information, we can calculate the distance using this formula. Rearranging the formula, displacement or distance is given as follows. Applying this, we can find the distance traveled between points A and B as 30 meters. We can follow the same steps to calculate the distance between points B and C. The distance between points B and C is 40 meters. The vehicle's total displacement is not simply the sum of the distances traveled, as it makes a right turn at point B. The paths from A to B, and then B to C, form a right-angled triangle, with the total displacement being the straight line distance, from the starting point A to the final point C. To find the displacement between points A and C, we use the Pythagorean theorem, stated as follows. Where S sub AB, and S sub BC are the lengths of the two legs of the right triangle. Substituting the values for the distances S sub AB, and S sub BC, we get the displacement from A to C as 50 meters. The average speed of a vehicle is determined by dividing the total distance traveled by the total time taken for the journey. In this scenario, we already calculated the total time taken, which is 13 seconds. To find the total distance traveled, we add the distance from A to B and from B to C. From A to B, the vehicle covers 30 meters, and from B to C, it covers 40 meters. Therefore, the total distance traveled is 70 meters. Now, using the total time of 13 seconds, we can find the average speed of the vehicle for the entire journey, which is approximately 5.38 meters per second. This value reflects the overall rate at which the vehicle covers the total distance, regardless of the changes in direction. To determine the average velocity of the vehicle, we need to consider the vehicle's overall displacement, and the total time taken during its journey. The overall displacement is the straight line distance from the starting point A to the final point C, which we previously calculated as 50 meters. Therefore, the average velocity of the vehicle for the entire journey is approximately 3.85 meters per second, in the direction from A to C. This value captures the vehicle's overall change in position, considering both the magnitude and direction of its movement. In this question, we've delved into the differences between average speed and average velocity, highlighting some key concepts that are crucial to understanding motion. Firstly, average speed is calculated by dividing the total distance traveled by the total time taken for the journey. This measure tells us how fast the vehicle is moving overall, without considering the direction. It simply quantifies the rate at which the vehicle covers the total ground along its entire path. Average velocity, on the other hand, is defined as the total displacement, divided by the total time taken. Displacement is the straight line distance from the starting point to the final destination, factoring in the direction of travel. As a result, average velocity not only indicates how quickly the vehicle changes position, but also reveals the direction of this movement. Alright, now that we've covered the distinctions between average speed and average velocity, let's move on to the next section, where we'll explore how to draw displacement time graphs when there's more than one moving object involved. In this section, we'll discuss techniques for representing multiple objects on the same graph, interpreting their motions, and understanding how their paths interact over time. This will help you visualize the movements and compare the behaviors of different objects simultaneously, providing deeper insights into their relative positions and speeds. In this scenario, we have two vehicles, A and B, both moving in the same direction. Vehicle A travels at a velocity of 10 meters per second, while vehicle B moves faster at 20 meters per second. Both vehicles pass a reference point, point O, at the same time. Our objective is to determine how far each vehicle has traveled, or in other words, their displacement, after 5 seconds. Both vehicles move with constant velocities, so we can use a displacement time chart to represent their motion clearly. Since both vehicles cross point O at the same time, we'll consider point O as our reference point for measuring both displacement and time. Now, why do we choose point O as the reference point? It's important to understand that the reference point doesn't necessarily have to be point O, we could choose any other point as our reference. However, selecting point O simplifies the problem because it's the point where both vehicles are located when we start measuring time. Choosing a different reference point could complicate our calculations unnecessarily, so it's crucial to place the reference point thoughtfully to simplify the process. In this case, point O serves as an ideal reference, helping us to keep our calculations clear and manageable as we analyze the motion of both vehicles. Next, let's draw the displacement time graph for both vehicles as they move past point O. Since both vehicles start from point O, this will be our origin for the graph, with time on the x-axis and displacement on the y-axis. Vehicle A moves at a velocity of 10 meters per second, while vehicle B travels at a faster velocity of 20 meters per second. These velocities determine the gradients of each vehicle's graph. On a displacement time plot, the gradient, or slope, of the graph reflects the velocity of the moving object. The steeper the slope, the higher the velocity. Since both graphs start at the origin, point O, we can plot each line according to the known velocities. Vehicle A, with a velocity of 10 meters per second, will have a gentler slope, compared to vehicle B, whose higher velocity of 20 meters per second results in a steeper slope. With the displacement time graph plotted, we can now derive two functions to mathematically express the motion of the two vehicles. These functions will represent how the displacement of each vehicle changes over time, based on their constant velocities. Since vehicle A has a velocity of 10 meters per second, we can express its motion using a linear function, where the slope corresponds to its velocity. Similarly, for vehicle B, which moves at a velocity of 20 meters per second, its function will also be linear, but with a steeper slope, reflecting its higher velocity. By deriving these functions, we can describe the motion of both vehicles precisely, and predict their positions at any given time. These equations will allow us to compare their displacements directly, and understand how their different velocities influence their journeys. With the two functions derived for the motion of the vehicles, we can now find the displacement of each vehicle at any given time. The beauty of these functions lies in their ability to provide precise information about the position of each vehicle as time progresses. For example, if we want to know the displacement of the two vehicles after 5 seconds, we simply substitute 5 seconds for t in each of the equations. For vehicle A, this substitution will show that it has traveled 50 meters, while vehicle B, moving faster, will have covered 100 meters. These functions aren't just limited to finding displacements. If we know a specific displacement, and want to determine how long it takes each vehicle to reach that distance, we can rearrange the equations to solve for time. By substituting the known displacement, we can find the exact time it takes each vehicle to travel that distance. This approach gives us a flexible tool for analyzing motion, allowing us to explore the relationship between time, displacement, and velocity for both vehicles in various scenarios. Now that we've explored how to draw displacement time graphs when dealing with two vehicles, let's move on to the next example with a slight twist. In this scenario, we again have two vehicles, A and B, moving in the same direction, with velocities of 10 meters per second and 20 meters per second, respectively. However, unlike the previous example, this time vehicle A is 50 meters ahead of vehicle B at the moment we start measuring time. Our task is to determine how long it will take for vehicle B, moving faster, to catch up and overtake vehicle A, as well as the distance that vehicle B will travel before overtaking vehicle A. Let's dive into this analysis and use the displacement time graph to find out when and where the overtaking will occur. To begin solving this problem, we need to decide on a reference point for our measurements. In this scenario, we have two options. We can either take measurements from the position of vehicle B or from vehicle A. Let's first consider using vehicle B's position as our reference point and see how the graph will look in this setup. When we take measurements from point B, all distances measured to the right will be considered positive, while distances to the left of point B would be negative. However, since all motion is to the right of point B, all displacements will be positive, and the graphs will be plotted entirely in the first quadrant of the Cartesian plane. Now, since we are measuring from vehicle B's position, the displacement of vehicle B will be 0 at the initial time. On the other hand, vehicle A is already 50 meters ahead of vehicle B at the start, so at time equals 0, vehicle A's displacement is 50 meters, in the positive direction. Let's plot these initial positions on the graph. From these points, we can then draw the displacement time graphs for both vehicles to visualize their motions and determine when vehicle B will catch up to vehicle A. As the two vehicles move, there comes a moment when vehicle B, with its higher speed, catches up with vehicle A. This event is visually represented by the point where the two lines intersect on the displacement time graph. To determine the exact time and displacement at which vehicle B overtakes vehicle A, we first need to express the equations of the two lines. Since the gradient of each line corresponds to the velocity of the respective vehicle, we can use this information, along with their starting positions, to derive the equations. The intersection point of the two lines represents the moment and location where vehicle B catches up with vehicle A. At this point, both vehicles have covered the same displacement, so we can set the two equations equal to each other to solve for the time it takes for vehicle B to overtake vehicle A. We can substitute the time into the equation for vehicle B's motion to determine the exact distance that vehicle B travels to catch up with vehicle A. This approach allows us to pinpoint the precise moment and location of the overtaking, confirming our results using both graphical and algebraic methods. Initially, vehicle A was 50 meters ahead of vehicle B. So, before vehicle B catches up, vehicle A continues moving forward, covering an additional 50 meters. This distance is represented on the displacement time graph. Now let's shift the reference frame from vehicle B to vehicle A We'll continue using the same sign convention, where any displacement measured to the right of the reference point is positive, and displacement measured to the left is negative. In this new reference frame, the graph will be slightly different. Unlike the previous scenario, where all displacements were positive, here we'll need to use both the first and fourth quadrants of the graph. Vehicle A's motion will be plotted in the first quadrant, as its displacement remains positive. However, since Vehicle B starts 50 meters behind Vehicle A, its initial displacement will be negative, placing it in the fourth quadrant. The velocities of both vehicles are still in the positive direction, so the gradients of both graphs will be positive, indicating that both vehicles are moving forward. First, let's mark the initial positions of the two vehicles on the graph. Vehicle A starts at the origin, and Vehicle B's position will be marked 50 meters below the origin, reflecting the 50-meter gap between them at the start. From there, we can plot their respective displacement time graphs to show how Vehicle B catches up to Vehicle A. What we can observe from these two examples is that, despite changing the reference frame from Vehicle B to Vehicle A, the actual displacement of the vehicles does not change. The positions and movements of the vehicles remain consistent, regardless of where we place our reference point. The difference lies in how we represent the displacement on the graph. In the first scenario, all the values were positive, whereas in the second, Vehicle B's initial displacement was negative. However, both graphs ultimately show the same result. This demonstrates an important concept in physics: displacement and motion are independent of the chosen reference frame. What changes is only the perspective from which we measure, not the actual physical quantities involved. Before we proceed with the video, I would greatly appreciate it if you could kindly give it a thumbs up, subscribe to my channel, and activate the notification bell. Your support means a lot. Thank you. Now, let's get back to the video. Before wrapping up this video, we'll explore one more example. In this case, we'll examine a scenario where two vehicles are moving in opposite directions, heading towards each other. This example will help us understand how to analyze situations where objects move towards one another, and how to represent their motions on a displacement time graph. By considering the velocities of both vehicles and their starting positions, we'll determine when and where the two vehicles meet. This setup introduces a new dynamic, as the vehicles' displacements will move in opposite directions, adding an interesting layer to our analysis. In this scenario, Vehicle A is moving towards Vehicle B with a velocity of 10 meters per second, while Vehicle B is moving towards Vehicle A at a faster velocity of 20 meters per second. At the moment we start the clock, the two vehicles are 90 meters apart. Our task is to find out how long it will take for the two vehicles to meet, and how far each vehicle will have traveled by that point. Since the two vehicles are moving towards each other, the gap between them will close quickly. By determining the time it takes for their displacements to equal each other, we can find out when and where the vehicles will cross. Both vehicles are moving at constant velocities, so we can express their motion using linear displacement time functions, making it straightforward to calculate the exact time and distance at which they meet. Just like we did in the previous examples, the first step is to choose a reference point to take our measurements. In this case, we can either choose point A or point B as our reference. Since it's often easier to work with positive numbers, we'll use point B as our reference point, where measurements to the right of B will be positive. In this scenario, we don't need to worry about measurements to the left of point B, as all motion is happening to the right. As a result, the graph will be limited to the first quadrant of the Cartesian plane. This makes it straightforward to track the displacements of both vehicles as they move towards each other. We'll begin by identifying the initial positions of the two vehicles. Since we've chosen point B as the reference point, the initial displacement of Vehicle B is 0, when time is 0. This corresponds to the origin of the graph. Vehicle A, however, starts 90 meters away from point B. Since all measurements to the right of point B are considered positive, Vehicle A's initial displacement will be marked on the y-axis at the 90-meter mark. This point represents vehicle A's position when time is 0. Both vehicles are moving at constant velocities, allowing us to express their motion using linear displacement time functions. However, it's important to note the difference in their velocity directions. Vehicle B is moving in the positive direction of displacement, meaning its velocity vector is positive. This results in a positive gradient for the displacement time graph of vehicle B. On the other hand, vehicle A is moving towards vehicle B, which is in the opposite direction of the displacement we're measuring. As a result, the velocity vector of vehicle A is negative, leading to a negative gradient for its displacement time function. By considering these gradients, positive for vehicle B, and negative for vehicle A, we can plot the motion of both vehicles on the graph, showing how their displacements change over time, as they approach each other. The point where the two lines intersect will represent the moment they meet. Since we already know the gradients of the two displacement time functions, along with their y-axis intercepts, which represent the initial displacements at time 0, we can now derive the respective functions for each vehicle. When the two vehicles meet, their displacements will be equal, at a certain distance from the reference point. To find the exact time at which this occurs, we simply equate the two functions and solve for time. Once we determine the time, we can substitute it into either function to find the distance at which the vehicles cross paths. This approach provides both the time and distance of the meeting point. Vehicle A moves a distance of 30 meters towards vehicle B, while vehicle B moves 60 meters towards vehicle A, before they cross paths. The total time it takes for both vehicles to meet is 3 seconds. I hope everything we've discussed thus far is clear. In summary, when objects are moving at constant velocities, displacement time graphs are particularly useful, compared to velocity time graphs. In this video, we've thoroughly explored how to apply displacement time graphs to analyze motion. However, in my next video, I'll be diving into the application of velocity time graphs and how they help in understanding changing velocities. So, make sure to click the bell icon to be notified when I upload that video. If you haven't already, I'd really appreciate it if you could subscribe to my channel, as it helps me continue creating more educational content. And if you enjoyed this video, please feel free to share it with your friends. Until we meet again in the next video, take care and goodbye.